Hello student. We in the last module we were discussing about the Rake receiver architecture. We have discussed several match filter based Rake receiver architectures, and we ended up with symbol basis symbol by symbol basis Rake receiver architecture design, where the decision in the receiver is going on the symbol by symbol basis basically, and we have done the analysis over a slow frequency selective fading channel for direct sequence space spectrum communication. In continuation of that, today we will learn and discuss a little bit more about the performance of this Rake receiver. Let us consider that we are using BPSK symbol. It is a data modulation running with binary, antipodal or PSK signal. So, then only a single symbol of waveform S1T will be associated with us. We do not have anything else. So, do you remember we considered the analysis in the last module as if that we have an M array signals, and the signals inside that array varies from hence S1T to SMT. If it is a BPSK signal, we have only a single bit going over one basis function, and hence the signal is consisting of only S1T. Hence, the decision variable will be also single, and only U1T will be correspondingly, and that is decision variable will be associated with the L number of the multipath components that is received with respect to single symbol transmission. After down conversion of this S1T, the BPSK modulated signal, the down converted signal will be looked like the equation 1-11. It is nothing but we understand that V1T was remember we started with a signal VKT that was received, that expression for VKT is there in the last equation in the last module. VKT was looked like this, remember, where my t was the symbol duration, and for which was the symbol duration, and the t can vary from capital T plus Td we wrote, Td is the delay, and so t plus Td up to that the signal can vary, and we have capital L number of the multipaths. So, the signal at the output of the receiver will be the combination of all the L number of the multipaths you are receiving signal over all L number of multipaths, where the Ci for each and every path I, Ci is the coefficient of the channel, complex coefficient of the channel getting introduced, T tau I is the delay, multipath delay associated with the ith multipath. So, this is the multipath delay associated with the ith path. This is the channel coefficient, complex channel coefficient associated with the ith multipath, and like that you are having capital L number of the multipaths, capital L number of the Ci values and Ti values you are having for each and every S. In our situation, Sk is having only single signal. So, we are having S1 only. So, correspondingly Vt will be V1 only. Hence, I have written in the equation 1-11 that the received signal will be the real part of this V1t to the power j 2 pi fct plus some noise associated with it. And now, actually after receiving it, you are coming down here, the NT is a zero mean white Gaussian noise process that that you have received, and this was a received signal, and then again you have multiplied with e to the power minus j 2 pi fct to bring it down. For the down conversion, this section came. And now, let us consider two things. Number one is, let us substitute a value mod Ci as alpha. I told that Ci is a complex quantity. So, we will take a mod value of it, and then we are defining a new symbol as alpha I, and we understand that k is equal to 1. So, we will put all these values slowly here, and we also saw that the maximum, the I, the delay will be given by I minus 1 by W, and so for the first one the delay will be 0, and the next one onwards the delay will be coming as a part of the this following this equation, where 1 by W is time duration of the match filtering, operation, and W is the bandwidth of the signal as well as actually bandwidth of the matched filter. And if I substitute now all this expression in this 1.11, and finally actually if we try to put the value of all this in the expression of this 1.6 that we developed in the last module, then finally we will be ending up with this decision variable as 1-12, where alpha I will be given by mod of C I. Ni is associated with, capital Ni is associated with the noise samples for each and every, associated with each and every path. And so we are getting actually the two halves, and this is the total decision variable based on which actually the output of the receiver will take the decision about which signal was transmitted, 0 or 1. And so if I see the output, we will be seeing the last equation that the Rake receiver produces a maximum ratio combining, and the conditional bit error probability for the maximum ratio combining, hence which is a probability given by the alpha I, will be given by this expression, where this gamma b is basically the individual, the instantaneous SNR of each and every path, and then you have taken the summation of all the overall the paths, and gamma I, the SNR, instantaneous SNR of each and every path, is given by signal power by the noise power multiplied by alpha I square. So, sigma into epsi into alpha I square by n0, where epsi is a reduction in the total alpha I. Epsi is the signal power multiplied by with the amplitude or the power of the it is a power of the channel coefficient that we are getting. So, basically it is a reduction of the signal power that you are taking in the top, and there is a noise power in the bottom. And see, in the Rake receiver we understand there is this alpha I associated with the computation of the signal power, final received signal power. It is actually will be different for the different multipaths, that is why it is having a variation over I. So, we need to find out the mean value of I, and therefore, actually this is the parameter who will largely deviate the computation of this bit error probability in the receiver that we understand. If in a practical scenario, most of the cases we understand that these channel coefficients are Rayleigh distributed, and if it is so, then this power, this SNR value, the gamma I, the SNR of each and every path will be exponentially distributed, and it will have the exponential probability density function given by the expression 1-15. Remember, in the exponential probability density function, we have got a factor called gamma I bar. This is the average SNR value that we will discuss next here. This average SNR for a bit in a branch I, that will be given by this, where actually the power is calculated. See why this is called average SNR, because we understood that the alpha I values largely values over if the multipath number changes. So, it is the alpha I square, and we are taking the mean value of it, and then you are calculating the over the mean channel power, you are multiplying with the actual signal power to get the equivalent signal power or received signal power at the end of that path, at the front end of the receiver. And remember, each of these multipaths also fades independently, so that this gamma I is statistically independent. And if this is true, that the gamma I is statistically independent from each other in each and every path, then gamma b can be expressed as a sum of all these independent and exponentially distributed random variables. So, then in such situation, the probability density function of gamma b will be given by this, where actually this factor A I will be given by the another expression written in 1.18. The bit error probability, it is determined by averaging the conditional bit error probability, which is this, and over the density given by this expression we have seen in the last slide. So, if I go on deriving it, and then over the whole L number of the multipaths finally. So, our derivation yields that the error probability will be finally the summation. If all the paths SNRs are independent to each other, then it can be given by the summation, and finally the derivation will lead us to the equation 1.20 for computation of the bit error probability for a BPSK kind of situation. Now, some good points to remember. The number one is that the number of the fingers in an ideal Rake receiver usually is equal to the number of the significant resolvable multipath components. But in practice, we understand that it is continuously changing in a mobile communication receiver, and then instead of attending the variable or dynamically choosing the number of the fingers on the fly in the practical communication system, what we do is actually we fix it to a high number, and out of those high number of the fingers, for currently how many number of the fingers are giving the significant result, we try to combine them only in the combiner. And that is a generalized selection diversity that entitles of selecting this LC number of the strongest resolvable multipaths among the all capital L available number of the multipaths. And then we can actually combine the maximum ratio combining in the receiver or equal gain combining of these LC number of the strong multipath components to get the output of the Rake receiver. And L minus LC components are actually rejected because they are having the lowest SNRs. In order to combine it, in order to choose how many number of what will be the typical value of LC, we can put also a threshold on the SNR values, so that it will be helpful to choose those number of the multipaths having the SNR higher than the selected or the predefined threshold. Now, if the diminishing returns are obtained as LC increases, but for fixed value of LC, the performance improves as the L increases, because if the number of the multipaths are more and the resolvable capacity is also there in the Rake receiver, in the receiver architecture. So, the more number of the multipaths you can actually accommodate, the more channel energy basically you can capture, and it will helps a lot in the channel estimation process as well as in the detection. So, actually if a number of the capital L increases, definitely it is a probability that number of LC will also increase, and hence it is preferable to go ahead with the combination with the higher number of the multiple components. But remember, it involves huge complexity in the receiver. So, an increase of this resolvable number of the components is potentially beneficial also to us, as I have already explained, because it is caused by some natural changes in the physical environment, and these additional multipaths are coming up as that will help us actually in improving the signal to noise ratio into the receiver architecture. But remember one thing, as L is increasing due to an increase in the bandwidth W, it is not beneficial. Means L can increase in two ways, right? One is actually there are some changes has happened in the scattering environment, that is why, and another point is because that W has changed. So, if it is change is because of the W only, then it is not a good situation for the receiver. And if it is from the multiple paths actually happening from the environment, then it is beneficial, because some of the paths may give a very good return after reflection. So, some new components provide some additional diversity in such cases, but they can exhibit some favorable Rayleigh fading also, because rather than the Rayleigh fading, and hence that average power per the multipath component in that cases, if it goes from the Rayleigh to the Rayleigh distribution, the component which will be decreasing, because some composite components fragment into more numerous, but the weaker components kind of. And so, if it happens like this, the estimation process of the channel parameters, they become much more difficult, and the fitting of this multipath components may be highly correlated also. We remember the whole computation of the error probability in the last few slides, that totally depends on the fact that all the multipath components are getting received, they are all independent to each other. That is why we can combine them independently, they can be processed independently, and there is no correlation to each other. But if it happens that the Rayleigh fading has changed to the Rician because the new components have got added from the environment, and that addition is such that they are highly heavily correlated to each other. Then the fundamental assumption will be lost, and then all the components won't be independent anymore. Okay. The estimation of the channel parameters needed here in a Rake receiver, it becomes more difficult as the fading rate increases. So, when the estimation error is really very large. So, if you are happening to, if you are facing such kind of the environment where actually the fragmentation is occurring because of the weaker components, and your channel estimation is becoming it is a degrading factor such that the errors are very large. In that case, the use of the Rake receiver that avoids the channel parameter estimation, that should be avoided. So, MRC always requires the estimation of all those channel parameters coherently, and when estimation error is very high, in such cases MRC combination is not a good option to go ahead with. Preferably you please proceed with the non-coherent post detection, your equal gain combining procedure for the combiner circuit. And to form of this kind of the Rake receiver for binary signal, we can actually then replace the earlier architecture that we have seen in the last module by this architecture. So, all the taps are coming out, and finally, they are having the equal gain inside, they are getting added up in the equal gain combiner, and here is the decision variable which is taking the decision about the transmitted symbol. We can extend actually the error propagation and the error probability calculation by taking two orthogonal signals. We did it first with a BPSK, where the orthogonal, there is a single signal S1T only. Now, we are having S1T and S2T both, okay, for consideration. And so, such that these two orthogonal signals, they satisfy this equation. So, this was the last equation that we have talked about in the last module, and I told that this, in order to happen this, we have a certain condition. The conditions are such that the processing gain is very high, autocorrelation function is relatively very small, coherent compared to the TC, and over the duration of the TC, and such that this happens. So, in the Rake receiver, definitely corresponding to two signals, you will get two decision variables. And remember, the equations are coming such that this is the contribution from the noise component, and this is the computation, this is the contribution from the signal part. And remember, inside that whole, we can have the real part of the noise, and if I consider the real part of the noise and imaginary part of the noise, hence U1 will be divided into two halves. Decision variable for 2 also is having two parts, one is the real part of the noise, and also is the second part is from the noise also. Remember this second decision variable that we have shown, it has a central chi-square distribution with 12 degree of freedom. L is the length of the multipath channels, and hence the probability distribution of that guy can be represented by these two. These are the chi-square distribution, probability density function for chi-square distribution, and where the variance is denoted by this. And so, here we have reproduced the two parts once again. U2 is given by this term, and U1 is the decision variable which is given by this term, and we will be interested in proceeding with the portion of U1, because that is considering the signal section measure. And remember that in the previous slide, when we are considering the phase theta I is a unknown phase associated with the signal part, and this theta I is uniformly distributed over the duration of 0 to 2 pi. And also remember that we have a Rayleigh fading channel. So, alpha I is or the amplitude of the channel coefficients, they are distributed by the Rayleigh distribution only. And so, if it is a Rayleigh distributed, so alpha I cos theta I, alpha I sin theta I, they are having some zero mean and independent Gaussian distributions associated here in the equation 1.25. So, this is a real part of it and imaginary part of it, and both of them are having a zero mean independent Gaussian distribution. So, you will get, if it is a Rayleigh distribution, you will get a mean of it. So, U1 has an exponential distribution finally with a mean of this, where this is the average SNR for the branch number I, we understand, and we saw in the last slides that this gamma I bar is basically taking the mean of over the power of the, it is a mean power taken from the channel that is actually now controlling the received signal power. That is why the mean is about. And the statistical independency, now this alpha over this alpha I and theta I, that should be there, and if they are statistically independent, it implies also that the terms inside the UI, the probability density function of the UI, all the U1s, sorry not UI, U1s are, they are having some distinct values for each and every this I mean for each and every branch, and then actually this gamma I bar can be given with your capital N is equal to L. So, as an erroneous decision can be made if your U2 is coming greater than U1, that means the whole noise components are basically very high with respect to the U1. If this is the situation happening, then actually the error probability will be given by this expression. What are the independent components inside it? So, for example, Bi and all. So, we will be discussing it in the later slide. We will do the integrating by parts for computing and eliminating the inner integral, and we do some changing in the remaining integration variables, and some simplification will yield the equation 1-28. Remember that we consider that the output, the post detection equal gain combination is going on, it is not the MRC that is going on in the Rake receiver, and we will be ending up with the detection probability given by equation 1-28, where this Bi will be given by the another expression 1.29. Remember, actually this is the more compact and it is considerably easier to evaluate than the classical formula in a different way, and the classical analysis of this classical analysis of computing this probability of error over the L path, number of the paths, actually that the main difference of this classical one and this new one is basically if you substitute the value of this gamma I bar with 2 gamma I bar, you will be ending up with the new one. So, we started with only the 2 different orthogonal signals, we understand. So, if it is 2 orthogonal signals having in our hand, those 2 orthogonal signals, for 2 orthogonal signals the probability, the L will be now substituted with a value of 2, and then this PB2 will be simplified form will be like this. Remember, this gamma 1 bar is the average SNR over the path 1 and for corresponding to the signal 1, and gamma 2 bar is actually the path instantaneous SNR path actually corresponding to the value path number 2. And so, the path total having the 2 paths and actually combination of these 2 will be easier to understand over the whole path, and actually if my gamma 2 bar now finally if it is 0 and I am not combining the signal receiving from the second one, then I will be ending up with the expression like this, which is basically equal to the expression of the path 1, probability of getting the bit error rate over a single path basically. So, this result shows what? That the result illustrates that the performance of heavily degrades if we are not combining the information over the multiple paths. So, the error probability will be high over a single path arrival and decision taken over based on the single path, and error probability will be definitely less if you are combining the signal to noise ratio, or if you are combining the information basically over the multiple paths. So, the gain that is coming from the diversity, if you can combine it properly either by the EGC or by MRC, you will be finally ending up with the fact that the error probability will be reduced. Now, remember one thing, that when a Rake receiver, there will be a severe degradation actually, because one of these paths are giving the combiner output equal to pure 0, and it is not giving the desired signal component. And this not happening the desired signal component, even if sometimes it happens, even if the path is there, it no desired signal component may occur if you are combining sometimes by the EGC, by equal gain combiner, and then rather than MRC, because MRC each and every path is estimated, the parameters are estimated and the combination goes on. So, when the error probability is high, and if we understand that there is the existence of the multiple path, even after that this is happening. So, we may actually need to take a call whether we should go ahead with the choice of EGC combination, or we will switch towards a MRC. And in the absence of this desired signal component, this input contributes only the noise to the combiner, and for the large values of gamma 1 bar, this extra noise causes an extreme loss of around 1 dB kind of. So, what we did actually in this Rake receiver, that we tried to establish in this module, we tried to establish the fact that if we are having BPSK signal and only single waveform is there, where we are ending up with, actually target was to calculate and see the error probability with this Rake receiver architecture. Then we tried to extract the signal, we tried to understand actually which kind of the combiner will be based for what kind of the scenarios, if the number of the multipass are increasing, where the MRC will be the good way to opt, or EGC will be the good way to opt, and how actually this increment of the L is, whether it is a beneficial to us in the signal combination and detection, or it is not. In that cases, we have suggested to use EGC if the capital L is increasing heavily. And then we have considered that instead of one orthogonal signal, if we are having two orthogonal signals, and how this decision variables will keep on changing us, and how the decision variable will be changing, and how finally the error probability will be affected. And if actually the signal component, I mean the effective signal component is not detected at the output of the combiner, what we have already signified here, that what is the effect of the noise that will lead us to the extreme changes, or actually it will cause how much amount of the changes can happen, or the losses can happen on the detection process. And we found that approximately 1 dB loss is expected to happen in this situation.